Hello, everyone. Today we'd like to give you a talk about the optimization of settlers and food supply for Mars mission. My name is Peyton Seaballs.
My name is Rishan Yang.
And my name is Wufeng Tian. I'm the faculty mentor for this project.
First, we will give you a brief introduction of our research project background. Then we introduce our modeling assumptions, which we had to figure out to make sense of the Mars mission. Then we will discuss the demographics and individual characteristics of the first crew being flown to Mars. From there, we will discuss what food should be brought to Mars that will feed our flight crew. Finally, we will explain our discussion from our research and work that could be done in the future. Before we can explain why scientists want to colonize Mars, we would like to give a brief introduction about the history of space exploration. Starting in 1957, the Soviet Union launched Sputnik 1 into outer space, creating the race to space for the United States. Within the last 63 years, scientists have been able to change space travel from thankfully getting humans into space to having humans living in space, growing food, and having satellites fly out to Pluto, which is 3.1857 billion miles away from Earth. After accomplishing all of these almost impossible tasks, what is stopping scientists from colonizing another planet? Colonizing another planet can be important for many reasons, but the biggest reason is colonizing another planet can decrease the likelihood of human extinction. Mars is the most similar to Earth with almost the same size and tilt, so seasons would be about the same. The Martian day is almost the same length as an Earth day, 24 hours, 39 minutes, and 35.244 seconds. Also, rovers have found water in the form of ice on Mars. However, it is a 7-month journey to Mars. Even though there are similarities, there are many challenges to living on Mars, such as there's less than 1% of oxygen on Mars, the average temperature is negative 80 degrees Fahrenheit, and gravity is 38% of Earth's, so it doesn't have a strong atmosphere. Before we can even think about studying the mission to Mars, these issues need to be resolved, which leads us to the modeling assumption. So a few assumptions need to be made before we consider the Mars mission becoming a reality. First, we need to assume that an atmosphere will be created, the temperature will be higher, and water will be more accessible. As we know that without the atmosphere, Mars will continue to be a cold, dry place where life cannot flourish. According to the existing research articles, scientists believe they may create a magnetosphere, which can create a stronger atmosphere by placing a magnetic shield at L1 orbit, which is shown in the figure. This will allow the atmosphere to become stronger and also shield Mars from sun radiation, which can start to heat up the planet and reduce temperature extremes between day and night. An aid to heating the planet will be releasing the greenhouse gas fluorine because it is 1,000 times stronger than carbon dioxide in heating up a planet when released in large amounts. The heating up of the planet will help the melting of the 20-kilometer lake of water stuck underneath ice, but something could be dropped on the lake to allow the water to escape faster. With all these issues assumed resolved, we can continue on with our mission to Mars.
Our first goal of this project is to determine the demographic and individual characteristics of the first group. 5 key characteristics of an astronaut are being resilient, adaptable, curious, trustful, creative, or resourceful. As considering the demographic and characteristic of the first flight crew members, not to mention that they should have the characteristics mentioned above. There are other issues that should be considered regarding the flight crew's demographic and individual characteristics. For example, age. We think the first crew should be aged between 18 to 67. 18 years old is the age that children become legal adults in most countries. We believe it would be wise to exclude senior people due to health concerns. However, if both parents in a family are selected, then the children will be allowed to come with. Equity, diversity, and inclusion will be one of our guidelines when we determine the demographic for first crew. We suggest that the first crew welcome candidates from any country in the world, since there are various expert and talented people all around the world. We believe a diverse community of flight crews is crucial and necessary. However, in order to effectively communicate, each flight crew member should be able to communicate fluently and effectively with a common language, for example, English. The point of this first flight crew is to settle down on Mars. So the younger the flight crew, the easier this will be. Before we can estimate the number of individuals needed for the first flight crew, we need to figure out the working time capacity and working time requirement. In a day, we do many different activities to keep us alive. We can estimate the percent of time spent on these various tasks, such as 33% is spent on sleeping, 80.3% spent on eating and personal care, so 41.3% is sleeping time. The rest of the time is considered working time capacity. However, we have to take into consideration children, elderly, and disabled crew members. So 25% of individuals will have to be taken from the working time capacity, leaving 30.1%. Working time requirement is the annual working time for settlers to survive on Mars. So industries will have to be created to allow survival. The equation shown on the slide states that the working time requirement has to be less than or equal to the working time capacity to ensure survival for the flight crew. While considering the working time capacity and requirement, we also need to consider the sharing factors because this will also take time, but can limit different industries to create more production. The working time requirement can be divided by the sharing factor equation for each domain to limit the working time requirement. There are 5 domains to worry about. Human activity can be divided into 5 domains: ecosystem, which are designed to maintain a healthy and sustainable habitat; energy, which can prevent the habitat from running out of energy and maintain energy supply; construction, which builds habitat, facility, and transportation; industry, which processes ores, produce materials, objects, and tools, manufacturing objects that are main purpose for this domain; and lastly, human domain, which is major activity in this domain, mainly concerns about social activities such as human interaction. Now, knowing all this information, the number of individuals needed for the first flight crew can be calculated. The equation used to take all 5 domains with the required working requirements, divided by their individual sharing factors set less than the working time capacity times the orbital period on the Mars to calculate the amount of people needed. The next 2 slides contains tables with the working time requirement for the 5 domains according to Jean-Marc Solotti's data, which was used in the equation to get the number of individuals needed. These are the first 2 tables of the time requirement in ecosystem and energy domain. These are the specific activity for each domain and specific hours required, and the sharing factor for each specific domain. These are the time requirements for the construction, industrial, and human domains. The graph shows where the working time requirements become less than the working time capacity, and where those lines cross is the number of individual needed, which comes to 140 individuals. So the graph, the red line, it's represent for working time requirement, and the blue line it's for working time capacity. So when the 2 lines cross, which you can see in the graph, it's 140 individuals, which this is how we get our minimum number of crew. And the working time capacity is due to the number of settlers. As you can see, the more of the settlers and the working time capacity rises. We also estimated the number of individuals required for each industry domain. According to labor force statistics from the current population 2021 survey provided by the US Bureau of Labor Statistics, specific number of individuals for each industry can be calculated. Ratio of essential occupations on Earth will also be applied for the crew to Mars. Therefore, our 140 flight crew members in each field will be calculated in the table, which we will need 35 people for ecosystem domain, 35 people for energy domain, 28 people for construction domain, 12 people for industry domain, and lastly, 30 people for human domain.
Within a day, humans need to consume a certain amount of calories to maintain their weight and receive the amount of nutrients that is healthy and will help them survive. So we need to calculate how many calories these 140 people will need to consume in one day and then expand that number to 1 year. The equation on the slide shows how to calculate how much calories a person needs to eat in a day based on their gender, age, weight, height, and activity level. We can estimate out of the 140 people that there will be 10 children, 65 women, and 65 men. From there, we can estimate that the average child will eat 2,500 calories a day, a woman 2,400 calories a day, and a man 3,000 calories a day. Then we also need to calculate the amount of nutrients needed to keep the travelers alive. The main three nutrients are proteins, fats, and carbohydrates. Of the calories eaten in a day, 30% should be protein, 55% carbohydrates, and 27.5% for adults should be fat, but for children, it should be 20%. The next slide shows the equation used to find the best amount of food needed to satisfy all the limits for the amount of calories, proteins, fats, and carbohydrates needed for the crew over a period of time. Given that the weight is a major concern when considering sending an object into outer space, we calculate the minimum amount of preservable food that needs to be sent from Earth before and during the trip for the first flight crew. Our objective function is to minimize the total weight of the food supply, while each food category needs to satisfy the calorie, carbohydrate, protein, and fat requirements. We have not considered the vitamins and minerals in this model since they can be provided via taking dietary supplements as in need. An optimized model can be set up as the following, where CI equals calorie, PI is the protein, FI is the fat, and BI is the carbohydrates. Using this equation, we need to decide on foods that will be preservable for long periods of time and have a variety to keep the morals high of the travelers. Food set before the flight crew will need to last the crew for a year, or at least until their crops have grown. Based on our optimization model, we found that the optimal amount of food is shown in the following table. There needs to be enough food to satisfy 137,240,000 calories, 122,372.7907 grams of carbohydrates, 63,228.29296 grams of protein, and 24,851.9586 grams of fat for this year. The table on this slide shows the food and the amount in pounds needed to be brought to Mars. The minimum amount of weight is 1,264,415.48 pounds. Now for the food being sent with the crew, it is the same concept, but the food will only need to last for 7 months. This means there needs to be enough food to satisfy 1,682,700 calories, 71,412.06693 grams of carbohydrates, 36,897.61 grams of protein, and 14,502.65 grams of fat. The minimum amount of food needed to be brought is 291,495.483 pounds, and the amount of each food is shown in the table on this slide. In the end, we figured that the first flight crew will need to consist of a minimum of 140 crew members, and the food will have a variety with the minimum amount of weight as the main factor. Astronauts do have special foods meant to be brought into space, but no flight crew has been this large. In the future, scientists will need to figure out how many people and when to send them to Mars, also how much food and at what intervals should be sent. Scientists also need to develop a plan for the Mars mission before any of these actions can be put into place. We believe our flight crew and food sent to Mars and the food sent with the crew is satisfactory to answer the question asked of us. Thank you.